the very limits of sight, 46 billion light-years away, the edge of our observable universe glows with ancient light, a whisper from when the cosmos was just 380,000 years old. That light has been stretched by the growth of space itself, its wavelengths now over 40 times longer than when they began their journey. Every galaxy you see is fleeing, and the farther it is, the faster it recedes, some already carried away faster than light by the swelling of spacetime. The universe is 13.8 billion years old, yet it is still expanding, with 68% of its energy coming from something we cannot see or touch, dark energy. But here's the question that bends the mind. If nothing exists outside the universe, what is it expanding into? Prepare to cross the horizon of the known into a mystery as vast as time itself. We begin. Imagine walking toward the horizon. Each step you take carries you closer to the place where Earth seems to meet the sky. And yet, no matter how far you walk, the line ahead always slips further away. The horizon does not exist as a wall or a boundary. It is a perspective, an illusion born of your position inside something vast. Now replace the rolling plains and the dome of blue with the whole of the cosmos. Replace the horizon with the farthest reach of light itself. This is the edge of the universe we speak of, an edge that does not exist in the way edges usually do. The question comes naturally, almost stubbornly. If the universe is expanding, what is it expanding into? The very phrasing assumes there must be something beyond, some empty field, some cosmic room into which space can spill. But here lies the paradox. Outside the universe, there is no outside. Space is not swelling into pre-existing emptiness. It is manufacturing the very stage upon which all distances are measured. In ordinary life, expansion means invasion, a gas spreading into a container, a wave rolling across a beach, a balloon stretching into the air around it. But the expansion of the universe is unlike any of these. There is no surrounding air into which our cosmic balloon pushes. The balloon itself is all there is, and its surface, representing space, is growing from within. If you were an ant crawling across that surface, you would feel the distance between you and every other ant increasing, yet you would find no center, no boundary, no destination. One of the strangest aspects of this reality is that there is no privileged vantage point from which to watch it happen. Every place in the universe is at the center of its own observable bubble. If you were on a distant galaxy billions of light years away, you would see the same pattern we see here, everything receding from you too. The same stretching of light, the same deep, cold silence in the gaps between galaxies. From any seat in the theater, the play looks the same. This absence of an outside is not merely a trick of language. It is built into the mathematics of general relativity, Einstein's grand weaving of space, time, and gravity. The equations do not describe a universe expanding into a container. They describe a fabric whose own measurements change over time. The growth is intrinsic. The meter sticks that define space grow longer without needing something to grow into. This is why scientists often reach for metaphors that break our normal thinking. The surface of a balloon, the raisin bread in the oven, a sheet of paper expanding while you draw upon it. Each tries to cut the cord that ties our thoughts to walls, boxes, and borders. We know this expansion is real, not because we watch galaxies physically racing through space like ships on a sea, but because their light is stretched as it travels. Edwin Hubble's observations in the 1920s revealed that the more distant a galaxy, the greater the redshift, the stretching of its light toward the longer, redder wavelengths. This redshift is not a Doppler effect from motion through a medium, like the siren of an ambulance shifting as it passes. It is the deepening of the very space between wave crests as the universe grows during the light's journey. Here's a scientific anchor. The observable universe is about 46 billion light-years in radius, far larger than the 13.8 billion years since the Big Bang might suggest. This is because space has been expanding during the travel time of light, carrying the sources of that light farther away, even as their photons raced toward us. You could say we are seeing a frozen, ancient image of the cosmos that no longer exists in that form, a living fossil made of light. And here's where things turn even stranger. If we imagine the universe as finite but unbounded, like the surface of a sphere, but in more dimensions than we can picture, then asking what's beyond is as meaningless as asking what lies north of the North Pole. There is no north-ier than north. There is no beyond. In such a geometry, traveling forever in a straight line could, in principle, return you to your starting point, though the distances involved dwarf anything the human mind is built to hold. But another possibility is that the universe is infinite. Not infinite like a field stretching beyond sight, but truly without end. A space with no repetition of edges, no walls, no limit to its reach. In such a reality, expansion doesn't mean more space being added to an infinite whole. It means the distances within it are growing. Galaxies that are already unimaginably far apart become farther still. There is no perimeter to push against. Instead, the scale of the entire fabric is changing. Here lies an odd, speculative thought. If the universe is infinite, and the laws of physics apply uniformly, then somewhere, unimaginably far away, there may be another region identical to ours, another Earth, another you, reading these same words in the same moment, simply because an infinite space allows for every arrangement of matter to recur. The distance to that twin is so enormous, about 10 × 10 × 115 meters, that it makes even our grandest scales seem like whispers, but in principle it is part of the same continuum we inhabit. And yet, for all our analogies, all our maps and measures, the expansion itself remains mysterious in essence. We can describe how it behaves. It is uniform on the largest scales, it accelerates under the push of dark energy, and it leaves fingerprints in the cosmic microwave background. But to answer why it is happening, why the universe's fabric is not static, is to step into territory where physics meets philosophy. Einstein once tried to hold the cosmos steady by inserting a cosmological constant into his equations, only to abandon it when Hubble's data forced the truth. The universe is dynamic. There are no cosmic walls rushing outward, no void outside waiting to be filled. Instead, there is the constant, quiet creation of new space between all things, a steady unweaving of the bonds that once held galaxies closer together. The further out we look, the further back in time we peer, until we reach a moment where space and time themselves were compressed into something smaller than the smallest grain of thought, a point where the idea of outside has no foothold. The paradox of the edge is, perhaps, only a paradox for creatures who evolved in rooms and forests and oceans, creatures for whom space was always a container. The universe is not a container. It is the thing in which containers have meaning. In this sense, expansion into nothing is a misunderstanding. The universe does not move into nothingness. It moves into itself. Beyond the faint edge of our observable sphere, light from more distant galaxies has not yet had time to reach us. They are not out there in a place we could walk to. They are in moments of time forever out of touch with our own. If the acceleration driven by dark energy continues, those regions will drift away faster than light can bridge the gap, their signals stretched into oblivion. The boundary of what we can know will shrink inward like a candle in the dark, even as the space around us grows without end. Perhaps the question, what is the universe expanding into, is like a mirror. When we press against it, it reflects our assumptions back to us. We expect edges because edges are all we've known. We expect an outside because we have always been inside something. To dissolve that expectation is to step, however briefly, into the same boundless perspective the equations suggest, a view where there is only the inside and it is infinite in its unfolding. We stand on no shore. There is no sea into which the cosmos swims. There is only the ever-widening fabric, and us, small but not separate, woven into its motion. Close your eyes for a moment and picture a vast sheet of fabric, smooth and still beneath your hands. Now, without pulling or stretching it from the edges, imagine that every thread within that sheet begins to lengthen at once. The weave loosens everywhere, equally, so that the entire cloth swells in all directions without needing to be pulled from outside. That is closer to what our universe is doing than any balloon or box could ever be. A growth that is not fed from beyond, but generated from within. In the world we inhabit, growth is usually parasitic upon something else. A tree rises by drawing nutrients from soil and energy from sunlight. A fire spreads by consuming fuel. Even a balloon expands by pushing against the air around it. But the growth of the universe defies this logic. It is not stealing space from somewhere else. It is manufacturing space itself. The distances between galaxies increase not because the galaxies are pushing through space, but because the space between them is being created in real time. This is why cosmologists often insist on that subtle but crucial distinction. The universe is not in space. The universe is space, along with time, bound together in what Einstein called spacetime. Asking where space is growing into is like asking where the surface of the Earth is printed upon. There is no paper beneath it. The surface is itself the stage. Think of a loaf of raisin bread in the oven. Each raisin is a galaxy, and the dough is space. As the dough rises, the raisins drift apart, not because they are moving on their own, but because the dough between them is swelling. The key difference, and it is a profound one, is that in the bread's case, the loaf swells into the oven air. In the universe's case, there is no oven. The loaf is all there is. We are raisins in an infinite bread that needs no pan to contain it. This strange form of expansion is written in the sky's oldest light, the cosmic microwave background. That pale afterglow is the echo of a time when the universe was just 380,000 years old and filled with a hot plasma of protons, electrons, and photons. Before that moment, light could not travel freely. It was scattered constantly by charged particles. But as the young universe cooled and atoms formed, photons broke free and began their unbroken journeys through expanding space. Over 13.8 billion years, the stretching of space has lengthened their wavelengths by a factor of about 1,000, turning once blazing light into a faint radio whisper at 2.7 degrees above absolute zero. The fabric's growth is literally etched into the light's change. And yet, if we focus too narrowly on what is measurable, we risk missing the conceptual leap that makes this possible. Space is not a fixed backdrop. It is a dynamic, malleable entity. Einstein's field equations describe how matter and energy tell space-time how to curve, and how space-time's curvature tells matter and energy how to move. But in a universe filled with matter evenly distributed on the largest scales, those same equations permit a more subtle behavior. The scale of space-time itself can change. This change is not an explosion, though the term Big Bang tempts us into picturing one. An explosion has a center and throws debris into pre-existing emptiness. The universe's expansion has no center and no pre-existing void to receive its contents. Instead, every region grows in lockstep, like the rising of bread or the uniform swelling of that imagined fabric. Here's a grounding fact. Observations of distant supernovae, particularly type Ia supernovae, those perfect cosmic standard candles, reveal that the rate of this expansion is not slowing under the pull of gravity as once thought, but accelerating. This discovery in the late 1990s shocked cosmology. Something unseen, dubbed dark energy, appears to be driving the expansion faster and faster. Its nature remains one of the deepest mysteries in physics, and its effect is that the universe is not only creating new space, but doing so at an ever-increasing pace. This leads us to an odd possibility. In the far future, distant galaxies will slip beyond our observable horizon. Light from them will never reach us because the space between us will expand faster than photons can cross it. To our distant descendants, the cosmos will appear emptier, the night sky stripped of all but the few galaxies gravitationally bound to our own. Expansion will continue, but knowledge of that expansion will fade, erased by the very process that creates it. The speculative twist here is subtle but tantalizing. If space can create itself, could it ever do so in pockets disconnected from ours? Inflation theory suggests it could, that the early universe may have undergone such rapid expansion that different regions became causally separated forever. Some versions of this idea, called eternal inflation, imagine that bubble universes like ours could be forming endlessly in a greater multiverse. Each bubble would contain its own space and time, swelling from within, utterly unaware of its siblings beyond a horizon it can never cross. And yet, in the mathematics, this is not magic. Expansion arises naturally when the energy density of space, the amount of energy stored in the vacuum itself, has certain properties. In our universe, the vacuum is not empty, it seethes with quantum fields. If, though, C fields have a constant energy density, then more space simply means more vacuum, which means more energy, which means more expansion. The effect feeds itself and the fabric grows. The difficulty is not in writing these equations, but in truly feeling them. Our senses evolved to measure distances that stay put. To us, a meter is a meter, a mile is a mile. We can imagine motion through space, but not space itself swelling beneath our feet. And yet, it is happening, not just out there in the black beyond the stars, but here, between you and me, between the atoms of this page, between the particles in your body. On the tiniest scales, the effect is overwhelmed by forces like electromagnetism and gravity, but on the grand scale, it dominates the fate of everything. This is perhaps the most humbling truth of it. We are not separate from the expansion. We are not passengers in a growing container. We are threads in the cloth that is weaving itself larger, moment by moment. There is no center to point toward, no edge to approach. The act of creation is everywhere, always, equally, and we are part of it. One open question remains at the heart of this. Why is there something about the universe that allows for this self-creation? Why does the vacuum have the energy it does? If dark energy is truly constant, the expansion will continue forever. If it changes over time, growing stronger or weaker, the destiny of the cosmos could be utterly different. We can measure the rate, we can predict the consequences, but the cause remains veiled. The paradox of what is it expanding into begins to dissolve when we accept that expansion is not a motion into emptiness, but a redefinition of distance itself. Space creates more of itself because that is what its laws dictate. The universe is not consuming an external nothing. It is multiplying its own being. In a way, it is a self-cause. contained act of Genesis, ongoing and eternal, at least until the physics that governs it decides otherwise. And so we drift outward on a tide that has no shore, each moment carrying us into a future defined by more space than the moment before. There is no container to fill, no outside to conquer. There is only the inside, and the inside is infinite in its capacity to grow. Long before galaxies spun their first spirals, before stars ignited with nuclear fire, before even atoms dared to form, there was only a universe that could fit in its entirety into a space smaller than a grain of sand. In that moment, there were no edges to speak of, no distances to measure, and no directions to choose from. Space and time themselves were newborn, their meanings not yet fixed. This was the first flicker of expansion, the beginning of the unfolding we now call the cosmos. To imagine it, we must strip away every instinct learned from the world around us. The birth of the universe was not an explosion in the traditional sense. There was no outside for matter to rush into, no silent void waiting to be lit. The Big Bang was an expansion of everything from everywhere, all at once. At time zero, a point in our mathematics where our physical theories strain and break, density and temperature were so extreme that the very laws we rely on today blur into uncertainty. This is where our instruments of understanding falter, but our models still point the way. In the first millionth of a second, temperatures reached trillions of degrees. Energy condensed into a storm of fundamental particles, quarks, electrons, neutrinos, each too hot and too restless to bind together. Space itself was in chaos, roiling like the surface of a sun magnified to infinity. The scale of the universe was tiny, but the speed of its transformation was incomprehensible. Every fraction of a second brought a doubling of size, a cooling of temperature, a shift in the very nature of reality. And here is the first anchor of certainty. About 13.8 billion years ago, this expansion began. We know this not by direct observation. No telescope can peer into that first instant, but by tracing the echoes it left behind. Every galaxy's light, stretched by the swelling of space, carries a timestamp. The faint afterglow of the cosmic microwave background is a fossilized image of the universe when it was just 380,000 years old. The ratios of light elements, hydrogen, helium, lithium, match the fingerprints of nuclear reactions that took place in the first few minutes. These threads weave a picture that points backward, converging on a single, searing origin. But even in those first flickers, the seeds of future complexity were already present. Tiny fluctuations in density, ripples in the primordial plasma, would become the scaffolding upon which galaxies formed. Imagine the surface of a pond whipped by an unseen wind, slight peaks and valleys forming in the water. As the universe expanded and cooled, gravity amplified those ripples, pulling matter together into knots and filaments, the cosmic web we see today. One might ask, what caused the expansion to begin at all? Here we enter the realm of the unknown. The standard Big Bang model does not explain why it happened, only that it did. Some theories point to quantum fluctuations in a pre-existing state, a moment when uncertainty gave birth to a surge of energy in space. Others lean toward the idea that the universe's beginning was not truly a beginning, but a transition, a bounce from a prior state we cannot yet probe. In these scenarios, the expansion we see is one chapter in a story without a first page. Even stranger is the notion that time itself began with the Big Bang. If this is true, then asking what happened before is meaningless. There was no before, only the timeless state that gave way to time. The expansion was not an event within time, it was the event that created time. This challenges the core of our intuition, for we are creatures bound to the arrow of time, carried forward by its flow. And yet, despite its strangeness, the first flicker of expansion followed rules, physical laws that have proven astonishingly consistent. Energy transformed into particles. Particles collided, annihilated, and created new forms. In the tiniest instance, forces like gravity, electromagnetism, and the strong nuclear force began to separate from the primal unity they once shared. Physics, in a sense, was crystallizing as the universe grew. Oddly enough, the earliest stages we can model with some confidence were already well past the moment of beginning. The curtain lifts for us only when the universe was a fraction of a second old, and even that fraction is separated from time zero by a gulf of ignorance. The singularity at the start is a signal that our equations cannot yet marry general relativity, which rules the large, with quantum mechanics, which governs the small. The dream of a theory of quantum gravity, a single framework to describe all scales, is, in part, the dream of understanding that first flicker in full detail. There is also a speculative shadow in this picture. What if our universe's birth was just one of many? Some models suggest that new universes can emerge from quantum fluctuations, each with its own laws and constants. In this view, our Big Bang was not unique, merely the local spark of an eternal cosmic fire. We may never know if others exist, for their light will never touch ours, but the possibility lingers in the background of every equation. The sensory image of this time is beyond anything we can truly see. A sky without stars, filled instead with an opaque fog of plasma glowing hotter than any furnace. Space would have no familiar landmarks, only the uniform blaze of creation. There would be no sound in the conventional sense, for sound needs air, but there were pressure waves rippling through the plasma, the heartbeat of the newborn universe, whose faint traces are still imprinted in the cosmic microwave background today. The expansion, then, was not the gentle drift we measure now. It was a surge, an unstoppable blooming of space itself. Every tiny region of the universe was stretching, not from a center, but from every point at once. And in that stretching, the stage was set for everything. The birth of matter, the rise of galaxies, the eventual spark of life. We live in the slow echo of that first instant. The distances between galaxies may now widen at a measured pace, but their separation began in fire and urgency. Without that first flicker, there would be no stars to burn, no planets to orbit them, no observers to look back and wonder what it all meant. Perhaps this is the deepest connection we have to that moment, the recognition that everything we are, every cell, every thought, is made of matter forged in the first minutes of an expanding space. We carry in us the relics of the first light, the atoms built in that searing infancy. To contemplate the first flicker is to look into a mirror that reflects not just the past, but the fundamental reason there is a now at all. If the first flicker of expansion was the opening note of the cosmic symphony, inflation was the deafening crescendo that followed, a surge so violent and brief that it defies our ability to imagine speed, size, or change. In a fraction of a second, the universe grew by a factor so immense that writing it down feels more like poetry than mathematics. At least 1026 times larger in about 10 to 35 seconds. This is not expansion as we know it now. This was space erupting into itself at a pace so far beyond the speed of light that the concept of speed almost loses meaning. To understand inflation, we must step back and see why it was proposed at all. In the late 1970s, cosmologists faced puzzles that the standard Big Bang model couldn't resolve. One was the horizon problem. The cosmic microwave background, the oldest light we can see, is astonishingly uniform in temperature in all directions, differing by less than 1 part in 100,000. But according to standard expansion alone, regions of the sky on opposite sides of Earth are so far apart that light could never have traveled between them in the time since the Big Bang. How then did they end up so perfectly balanced in temperature and structure? Another puzzle was the flatness problem. The geometry of the universe appears to be incredibly close to perfectly flat. Even a tiny deviation in the early universe would have grown over billions of years into a curvature we could detect, but we see none. This demanded an explanation. And then there was the monopole problem. Particle physics predicted that in the high-energy conditions of the early universe, exotic magnetic monopoles should have been produced in abundance. Yet in all our searches, we have found none. Inflation theory, first proposed by Alan Guth in 1980, swept across these problems like a cosmic eraser. If, in its infancy, the universe underwent a period of runaway expansion driven by a peculiar form of energy in the vacuum, then all regions we see today were once close enough to share information, to agree on their conditions before being flung apart. Inflation would also stretch any curvature in space to near perfect flatness, much as the surface of a balloon appears flatter as it swells, and it would dilute any unwanted relics, like monopolies, to near invisibility. But the scale of this event is difficult to hold in the mind. Imagine a region of space smaller than a proton suddenly ballooning to macroscopic size, perhaps larger than the observable universe today, in less than the blink of an eye. This does not break the cosmic speed limit, for that limit applies to objects moving through space, not to the growth of space itself. Inflation simply pulled everything apart faster than light could keep up. The physics behind inflation lies in a hypothetical field called the inflaton, a cousin to the fields that produce forces like electromagnetism. In certain conditions, this field could store enormous potential energy, acting like a spring wound to impossible tension. When released, it would drive exponential expansion. Eventually, the field would decay into a hot bath of particles and radiation, a process called reheating, giving rise to the familiar hot Big Bang phase that produced the first atoms, stars, and galaxies. Here's a factual anchor. Evidence for inflation is indirect but compelling. The tiny fluctuations in the temperature of the cosmic microwave background match the statistical fingerprint of quantum fluctuations stretched to cosmic scales by inflation. This is one of the most extraordinary implications, that the seeds of galaxies may have been born from subatomic jitters in the vacuum, magnified to astronomical size in a heartbeat. Speculation takes us further. Some versions of inflation, known as eternal inflation, suggest that while inflation ended in our region, it may continue in others. The result would be a vast multiverse, countless bubble universes budding off an eternally expanding backdrop. Each bubble could have different laws of physics, different constants, different destinies. We, inside our bubble, could never see the others, for the space between us and them grows faster than light could bridge. In such a picture, our universe is not the cosmos, but one chapter in an endless library. And yet, inflation is not without controversy. While it elegantly solves the horizon and flatness problems, and while it fits the observed data well, it remains a hypothesis. We have not yet detected the most decisive signatures, and it predicts a particular pattern of polarization in the cosmic microwave background caused by primordial gravitational waves, ripples in spacetime from the inflationary era. Some claimed detections, like the BICEP 2 announcement in 2014, later turned out to be contaminated by galactic dust. The search continues. Visually, to imagine inflation is to imagine all reference points shattering. There is no where to stand and watch. The expansion is everywhere, all at once. Picture an ocean that is itself the water, with no shoreline, suddenly surging outward in every direction. Distances that were once subatomic become billions of light years in the blink of an eye. The texture of space, once jagged and quantum, is smoothed almost to perfection. Oddly, inflation also reshapes our idea of time. If eternal inflation is correct, there may be no single beginning. Different regions would start and end their inflationary phases at different times, and in some, it may never stop. There would be no universal now, just an unending froth of birth and bloom on an infinite scale. And yet, from our perspective inside one such bubble, inflation ended long ago. The heat it left behind filled space with the ingredients for everything that followed. Without it, the sky might not be so uniform, galaxies might not cluster as they do, and life might never have found a stable stage. It is strange to think that we owe our existence not only to stars and atoms, but to a flash of expansion so fierce it outran light itself. Stranger still to think that this flash may have been one of countless others, each giving rise to universes forever hidden from one another. In the end, inflation remains one of the most profound ideas in modern cosmology, not because we have proven it beyond doubt, but because it dares to connect the smallest quantum tremors to the largest cosmic structures. It suggests that the smoothness of the night sky and the sweep of the galaxies are not accidents, but the stretched shadows of microscopic beginnings. And if that is true, then every saint you have ever seen, every galaxy you have ever imagined, began as a ripple in the void, a ripple that inflation carried from the realm of the subatomic to the stage of the infinite. Long after inflation's unimaginable surge had ended, the universe was still a seething, brilliant fog, a place where light itself was trapped. Space was filled with a dense plasma of electrons, protons, and photons, all locked in a constant, furious dance. Photons could not travel far before colliding with charged particles, scattering in every direction. It was, in every sense, a universe without transparency. If you could have stood in that era, you would see no stars, no galaxies, only a uniform, blinding glare. This was the cosmic dark age before there was darkness. The glow was everywhere, but it was not free to roam. The temperature of this young cosmos was around 3,000 degrees Kelvin, hot enough to keep atoms from forming. In such heat, electrons refused to bind to protons. The very building blocks of matter were locked in an endless separation, and without neutral atoms, light could not slip free. But the universe was still expanding, and with expansion came cooling. Over the course of 380,000 years since the Big Bang, the searing plasma thinned, and the temperature dropped just enough for electrons to finally merge with protons, forming the first stable hydrogen atoms. This event is known as recombination, though it was truly the first combination of its kind. And with this shift, everything changed. Suddenly, the photons that had been trapped were released. They began streaming through space, no longer constantly scattered, carrying with them a perfect record of the moment they were freed. This light has been traveling ever since, stretching with the expansion of the universe, cooling and reddening until it now reaches us as a faint glow at a temperature of 2.7 Kelvin, just a whisper above absolute zero. This is the cosmic microwave background, the oldest light we can see, a fossilized photograph of the universe in its infancy. It fills all of space, bathing every direction with the same faint radiation. First detected accidentally in 1965 by Arno Penzias and Robert Wilson, who were awarded the Nobel Prize for their discovery, the CMB confirmed one of the central predictions of the Big Bang theory. It is quite literally the afterglow of creation. To our eyes, unaided, the CMB is invisible. Its wavelengths are too long to see. But with the right instruments, we can map it in exquisite detail. And when we do, we find that it is astonishingly uniform, with tiny fluctuations in temperature on the order of 1 part in 100,000. These small variations are not noise. They are the seeds from which all structure in the universe grew. Regions that were slightly denser in the early plasma would, under the pull of gravity, gather more matter over billions of years, eventually forming galaxies, stars, and planets. In 1989, the COBE satellite, Cosmic Background Explorer, made the first precise measurements of the CMB spectrum, confirming that it was an almost perfect blackbody, exactly what theory predicted for light from the early universe. Later missions like WMAP, Wilkinson Microwave Anisotropy Probe, and the Planck satellite refined our maps of its tiny temperature fluctuations, allowing us to measure the age, composition, and geometry of the cosmos with extraordinary precision. From these measurements, we learned that ordinary matter, the kind that makes up stars, planets, and people, accounts for only about 5% of the universe's total energy budget. Dark matter, unseen but inferred from its gravitational pull, makes up about 27%, and dark energy, the mysterious driver of accelerated expansion, comprises the remaining 68%. These numbers are not guesses, they are read from the ancient light of the CMB itself. Speculation blooms from here. Some cosmologists have proposed that the pattern of fluctuations in the CMB could carry the fingerprints of other universes. In certain inflationary models, collisions between bubble universes could leave subtle, circular imprints in the microwave sky, faint bruises in the fabric of our own bubble. No convincing evidence of such imprints has yet been found, but the search continues. And yet, even without exotic explanations, the CMB holds deep mysteries. One of them is the axis of evil, a curious alignment of certain large-scale features in the CMB that seems to defy the expectation of perfect randomness. Whether this is a statistical fluke, an artifact of our instruments, or a hint of new physics remains unresolved. The CMB also carries with it an echo of the universe's sound. In those early days, the plasma was dense enough for pressure waves, cosmic sound waves, to ripple through it. These oscillations left their mark on the distribution of hot and cold spots in the CMB, much like the standing waves on a drumskin leaf, patterns you can both see and hear. We cannot listen to these ancient sounds directly, but by translating the data, scientists have reconstructed their frequencies. A deep, resonant hum in the range of 30 to 300 hertz, forever imprinted in the oldest light. Visually, to imagine the CMB is to imagine the entire sky glowing faintly, evenly, in every direction, like the dim embers of a fire that once burned everywhere at once. The glow is not coming from any particular place. It is coming from all places, from the edge of the observable universe itself. It is a wall of light, not because it blocks our view, but because it is the farthest wall we can ever see. Beyond it lies a time when the universe was still opaque, a realm forever hidden from direct observation. And here is where the philosophical weight settles in. The CMB is not just light from the past, it is the past. Those photons have been traveling for nearly 14 billion years without being absorbed or scattered. When they strike the detectors of our telescopes, they are completing a journey that began when the universe was young and unrecognizable. To look at the CMB is to look directly into the face of the newborn cosmos. It also draws a line we cannot cross. We can infer what happened before recombination through theory and indirect evidence, but we will never receive light from earlier times. The fog of the primordial plasma is an impenetrable curtain. Inflation, particle interactions, quantum fluctuations, all of these belong to a time before the sky became transparent, and we must reach them by mathematics and creativity alone. And yet, standing beneath the invisible canopy of the CMB, we are reminded that the universe does remember. It holds its history not in words or stone, but in the very radiation that bathes us, passing unnoticed through our bodies every second. It is a quiet, unending whisper from a time when everything we know was compressed into a blazing fog. The glow of the ancient sky is not simply a relic. It is the key to our understanding of cosmic origins. Without it, the Big Bang would remain a bold hypothesis. With it, we have a map, a clock, and a mirror, a way to trace our story back almost to the beginning, to see the first shapes that would one day become us. If you have ever stood in a wide, flat plain and turned slowly in place, you'll know the sensation. The horizon stretches evenly in all directions, and no matter where you look, it feels as if you are in the middle of it. Now take that feeling and expand it beyond the plains, beyond the Earth, beyond even the farthest galaxy you can imagine. That is the truth of our universe. From every point, it looks as if you are at the center, and yet there is no true center at all. The question arises naturally. If the universe is expanding, doesn't that imply it must be expanding from somewhere surreal? There must be a point of origin, a special place from which all else recedes. But the cosmos does not work like an explosion, throwing fragments into empty space. It is more like the surface of a balloon as it inflates. Every point moves away from every other point, and yet there is no single spot on the surface that is the center of expansion. The center lies in a dimension you cannot reach, outside the surface entirely. And in the case of the universe, there is no such outside at all. This is the first truth to absorb. The expansion of space has no preferred location. Every observer, no matter where they are, will see the same general pattern. Galaxies moving away in every direction, the more distant, receding faster. If you were transported to a galaxy 10 billion light-years away, your view of the universe would still show you at the center of your own expanding sphere. This is not an illusion. It is a direct result of the universe's geometry. Scientifically, this is supported by the cosmological principle, the assumption that on large enough scales, the universe is homogeneous, the same everywhere, and isotropic, the same in every direction. Observations of the cosmic microwave background and the large-scale distribution of galaxies confirm this to remarkable precision. The universe is clumpy on the scale of galaxies and clusters, but when averaged over hundreds of millions of light-years, it smooths out into an almost uniform soup. Here is an anchoring fact. The Hubble-Lemaitre law describes how the velocity at which a galaxy recedes from us is proportional to its distance. Double the distance, and the apparent recession speed doubles. This is not because galaxies are flying through space away from some central explosion, but because the fabric of space between us and them is stretching uniformly. An analogy often used is raisin bread in the oven. Each raisin is a galaxy, and as the bread dough rises, all the raisins move apart from one another. From the point of view of any raisin, it appears that all others are receding, and the farther away they are, the faster they seem to move. There is no single raisin at the center of the loaf. The process is everywhere. But the lack of a center is not just a curiosity. It has profound consequences for how we understand our place in the cosmos. In ancient times, humans often assumed Earth was at the center of the universe because it seemed that the sky rotated around us. That assumption was dismantled by observation, and with it went the idea of a privileged location. The modern view extends that dethroning to its ultimate limit. There is no favored place anywhere. The universe has no throne, no seat of creation, no cosmic capital. And yet, while the expansion has no center in space, it does have a center in time. All galaxies trace their recession back to a moment roughly 13.8 billion years ago, when the scale of the universe was much smaller and denser. That moment, the Big Bang, is not a location, but an event that happened everywhere at once. Every point in space today was once compressed into that same hot, dense state. Speculation takes this idea further. If space is infinite, then it was always infinite, even at the moment of the Big Bang. The expansion did not turn a finite space into an infinite one. It simply increased the distances between points in an already boundless fabric. In such a model, the idea of a central point becomes meaningless. There was never a single spot from which the universe grew, only a global swelling of an endless expanse. Oddly enough, this also means that the observable universe, the part we can see, is just a bubble within the whole, centered on us simply because light has had time to reach us from within that sphere. Someone in a galaxy far beyond our reach would have their own observable bubble, overlapping ours only party. Ally, and beyond both lies an expanse neither could ever see. The illusion of being at the center is a gift of perspective, not a sign of privilege. Here's an interesting twist. The uniform expansion means that space itself can carry objects away from each other faster than light, without violating relativity. This happens at great distances, where the recession speed caused by the stretching of space exceeds the speed of light. Those galaxies are not moving through space faster than light. It's the space between us and them that is growing so rapidly. This creates an event horizon, a limit beyond which light emitted today will never reach us, no matter how long we wait. The absence of a center also reshapes the question of destiny. If every point is equivalent, then the universe's fate, whether it ends in a big rip, a slow heat death, or a collapse, will happen everywhere, equally. There will be no place to hide, no cosmic edge to escape over. Visually, to imagine a centerless universe is to imagine floating in a vast, dark ocean dotted with lights. No matter which direction you look, the lights drift away, the more distant receding faster. There is no shore, no island, no hint of where you began. The motion is not toward or away from a fixed landmark. It is simply the natural unfolding of the ocean itself. And here, perhaps, is the most humbling perspective. The lack of a center means we are neither special nor insignificant in any absolute sense. We are part of a process that is the same everywhere, bound into the same rules that govern distant galaxies and unseen corners of the cosmos. The center is an illusion of our view, and giving it up frees us to see the universe as it truly is, vast, impartial, and without boundaries in space. In a universe without a center, every point is equally the middle of its own story. Ours just happens to be the one we can tell. Far out in the dark, beyond the reach of our Milky Way's spiral arms, the Great Drift is underway. Galaxies, each containing billions upon billions of stars, are gliding apart, carried not by their own propulsion, but by the steady swell of the cosmic tide. From the smallest dwarf galaxies to the colossal superclusters, every luminous island in the cosmos is taking part in this silent migration. From our perspective on Earth, this drift reveals itself in the stretching of light. When astronomers look deep into the night, they measure the redshift of distant galaxies, a lengthening of the light's wavelength caused by the expansion of space. The farther away the galaxy, the more its light is stretched, and the faster it appears to recede. This observation, first made systematically by Edwin Hubble in the late 1920s, was the evidence that turned the idea of an expanding universe from speculation into fact. Hubble's work revealed a pattern so consistent it was distilled into the Hubble-Lemaitre law. Recession speed is proportional to distance. This relationship is simple in form but profound in meaning. It tells us that the expansion is not just happening in isolated regions, but everywhere, all at once. Even the most distant galaxies we can see obey this cosmic choreography. Here's an anchor. Today, the Hubble constant, the measure of this proportionality, is estimated to be around 73 kilometers per second per megaparsec, using local measurements, though other methods, like those involving the cosmic microwave background, yield slightly lower values around 67 kelmas mpc. This discrepancy, known as the Hubble tension, is one of the most intriguing current debates in cosmology. If it persists, it may point to new physics beyond our current understanding. But not all galaxies are swept apart at the same rate. Gravity, the oldest sculptor of cosmic architecture, binds galaxies into clusters and clusters into superclusters. Within these gravitationally bound systems, galaxies can orbit one another, collide, and merge, resisting the general expansion. The Milky Way, for example, is part of the Local Group, a cluster of more than 50 galaxies dominated by the Andromeda Galaxy and our own. While most galaxies in the universe drift away from us, Andromeda is actually approaching at about 110 kilometers per second, pulled toward us by mutual gravity. In roughly 4 billion years, the two spirals will merge into a single, giant elliptical galaxy, a slow-motion dance lasting another few billion years. Beyond these local havens of gravity, however, the Great Drift dominates. The Virgo supercluster, home to our Local Group, is itself part of a much larger structure called Laniakea, a cosmic basin containing over 100,000 galaxies. Laniakea flows outward along the expansion, its galaxies riding currents that stretch for hundreds of millions of light years. The large-scale map of these motions reveals filaments, voids, and knots in the cosmic web, all slowly stretching apart. The expansion today is not the same as it was billions of years ago. For the first few billion years after the Big Bang, the pull of gravity from matter slowed the rate of expansion. But about 5 billion years ago, something changed. Observations of distant type Ia supernovae in the 1990s revealed that the expansion had begun to accelerate. This was the first evidence for dark energy, the mysterious force or property of space itself that now drives galaxies apart faster and faster. Dark energy makes up about 68% of the total energy budget of the universe. It acts uniformly, pushing on space in all directions. As more space comes into existence through expansion, there is more dark energy, and so the push strengthens. This feedback ensures that the Great Drift is not just continuing, but accelerating toward a future where galaxies far beyond our local cluster will vanish from view. Speculation takes this to extremes. If dark energy's effect grows without bound, the universe could end in a big rip, a scenario where, tens of billions of years from now, the expansion becomes so rapid it overcomes all forces, tearing apart galaxies, then stars, then planets, then molecules, and finally, the very fabric of spacetime. If dark energy remains constant instead, the cosmos will settle into a slow fade toward heat death, where all activity ceases in the far future. The drift also limits what we can ever know. Because the speed of light is finite, and the expansion of space can carry galaxies away faster than light can bridge the gap, there is a cosmic event horizon beyond which events can never affect us. In practical terms, This means that much of the universe, perhaps the vast majority, is forever beyond our reach. Even if we could travel at near-light speeds, space itself would outpace us. Yet, in the observable sphere we can still chart, the drift is a source of beauty as well as melancholy. The Hubble Ultra Deep Field image, compiled from hundreds of hours of observation, shows thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length. Some of these galaxies are so distant that we see them as they were more than 13 billion years ago. Their light stretched almost beyond recognition. They are ancient participants in the Great Drift, their present locations now unimaginably farther than where their light began its journey. From a sensory perspective, imagining the Great Drift is like standing on a raft in an infinite ocean, watching countless other rafts recede into the mist. The water itself is flowing between you, stretching the distances without any wind or current you can feel. You do not sense the motion directly, but the view changes inexorably. Oddly, while the drift separates us from most of the universe, it also connects us to its origin. Every recession velocity we measure, every photon stretched by the expansion, is a thread back to the Big Bang. The drift is not random. It is the natural unfolding of space-time itself. And here lies a quiet truth. The Great Drift is not something happening out there. It is happening everywhere, even between the atoms in your body. On those scales, the effect is imperceptible, overwhelmed by stronger forces. But on the scale of galaxies, and greater, it becomes the dominant motion of all things. In this sense, we are not merely observers of the drift. We are part of it. Our home galaxy is moving with it, our planet carried along in its spiral arm, every star around us woven into the fabric that is stretching. We are passengers on a journey whose destination remains unknown, carried on a current we did not choose but that defines the shape of everything we see. The stars and galaxies we see scattered across the night sky are only the visible tracery of a far grander structure. A delicate frost of light resting on the unseen scaffolding that holds the cosmos together. This scaffolding is made not of ordinary matter, but of something we cannot touch, taste, or see. Dark matter. It does not glow. It does not reflect. It does not emit any radiation we can detect. Yet without it, the universe as we know it would never have taken shape. Astronomers first suspected its existence in the early 20th century, when they noticed something strange in the motions of galaxies. In the 1930s, Fritz Zwicky, studying the Coma cluster, found that the galaxies inside it were moving so fast that they should have flown apart unless there was far more mass present than what could be seen in stars and gas. Decades later, in the 1970s, Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies and discovered a similar puzzle. The outer stars were moving just as fast as those closer to the center, defying the expectations of Newtonian gravity based on visible matter alone. Something unseen had to be providing the extra gravitational glue. Today, we estimate that dark matter makes up about 27% of the total energy matter content of the universe, more than 5 times the amount of ordinary matter. Its gravitational pull is the invisible architect of cosmic structure. In the early universe, dark matter began clumping long before ordinary matter could. While ordinary matter was still coupled to radiation in the hot plasma, unable to collapse under its own gravity, dark matter was already gathering into vast halos. These halos acted as gravitational wells into which gas could later fall, forming the first stars and galaxies. The cosmic microwave background, CMB, carries the imprint of this relationship. The tiny variations in its temperature map are shaped in part by the distribution of dark matter in the young universe. Without dark matter's early scaffolding, the seeds of structure would have been too small. Gravity would have been too weak to form galaxies in the time available. The night sky would be an empty darkness, dotted perhaps with a few lonely stars, but devoid of the grand spirals and clusters we know. But what is dark matter really? This remains one of the great open questions. We know what it is not. It is not made of atoms, protons, neutrons, or electrons. It does not interact with light or with the electromagnetic force. It seems to pass through ordinary matter almost entirely unhindered, interacting only through gravity and perhaps the weak nuclear force. One leading candidate is a class of particles called WIMPs, weakly interacting massive particles. These hypothetical particles would have been produced in abundance in the early universe and would still be drifting through space today, forming the halos around galaxies. Another possibility is axions, extremely light particles predicted by certain extensions of the Standard Model of particle physics. More exotic suggestions include sterile neutrinos, hidden sector particles, or even modifications to our understanding of gravity itself. Despite decades of searching, with experiments deep underground in space and using massive particle accelerators, we have not yet detected a dark matter particle directly. Detectors buried beneath mountains or submerged in tanks of liquid xenon wait patiently for the faintest sign of a collision between dark matter and ordinary matter. So far, the silence has held. And yet, the evidence for dark matter's gravitational influence is overwhelming. We see it in the way galaxies rotate, in the motions of galaxy clusters, in the bending of light by gravitational lensing. Entire arcs and rings of light around massive clusters, captured in telescopic images, are shaped by the invisible hands of dark matter, bending space itself. In some cases, these lensing effects reveal more dark matter than visible matter by orders of magnitude. Dark matter does not act alone in shaping the cosmic story. Its counterpart, dark energy, governs the large-scale expansion of the universe, while dark matter rules the realm of structure formation. Together, they form the invisible foundation upon which the visible universe is built. Dark matter pulling galaxies together, dark energy driving them apart. Speculation about dark matter's nature reaches into the strange territory of physics beyond our current reach. Could it be made of primordial black holes formed in the first moments after the Big Bang? If so, their masses would have to fall into narrow ranges to avoid contradicting other observations. Could it be a shadow version of ordinary matter, complete with its own forces and particles, interacting with ours only via gravity? In such a scenario, there might be entire dark galaxies we will never see, moving alongside ours through the cosmic web. Speaking of the cosmic web, dark matter is its very backbone. Computer simulations of the universe's evolution, starting from the initial conditions mapped by the CMB, show vast filaments of dark matter stretching across hundreds of millions of light years. At the intersections of these filaments lie clusters of galaxies, shining markers of the invisible highways of mass. Between the filaments are enormous voids, sparsely populated with matter of any kind. If we could somehow see dark matter, the universe would look utterly transformed. Instead of isolated islands of light in a dark sea, we would see a vast, interconnected lattice glowing with the true mass of the cosmos. Ordinary matter would appear only as a faint frosting along these immense strands. And here is a humbling truth. We are built on this invisible foundation. Every star in the Milky Way, every planet, every molecule of our bodies resides inside a halo of dark matter that has existed for billions of years. We orbit its gravitational heart without ever feeling its presence directly. We are, in a sense, ghosts living within a larger ghost. The hunt for dark matter is not only a quest to understand the universe's structure, but also to uncover the physics of its earliest moments. Whatever dark matter turns out to be, its properties will tell us about conditions in the universe just fractions of a second after the Big Bang, conditions we cannot otherwise recreate. For now, dark matter remains a silent partner in the cosmic dance. We trace its steps through the motions of galaxies, through the warping of light, through the structure of the cosmic web. It has no color, no warmth, no sound, but without it, there would be no stage for the luminous drama of stars and galaxies. It is the architect whose work we can see, even if we can never shake its hand. The expansion of the universe is not a neutral backdrop to cosmic history. It is the clock that ticks toward the T of all things. From the moment space began to stretch, its pace has dictated what structures could form, how long stars could shine, and how the distant future will unfold. The laws that govern this expansion are, in a very real sense, the laws that decide destiny. In the earliest ages, gravity reigned as the dominant force. Matter, both ordinary and dark, pulled on itself, slowing the outward surge of space left over from the Big Bang. Galaxies could form only because this slowdown allowed clumps of matter to collapse and ignite. For billions of years, the cosmic tug-of-war between gravity and expansion shaped the universe. But then, about 5 billion years ago, something shifted. Instead of continuing to decelerate, the expansion began to speed up. This reversal was first revealed in the 1990s by teams studying distant type Ia supernovae, those stellar explosions bright enough to serve as cosmic mile markers. By comparing their intrinsic brightness to how dim they appeared from Earth, astronomers could measure distances across billions of light years. The data showed a startling pattern. Far-away supernovae were dimmer than expected, meaning they were farther away than they should have been if the expansion were slowing. Space was not only expanding, it was accelerating. The cause of this acceleration has been given the name dark energy. We know almost nothing about its nature, but it behaves as if it were an intrinsic property of space itself, exerting a constant repulsive pressure. As space grows, there is more of it, and so the total push increases. This explains why the expansion rate has begun to dominate over gravity on the largest scales. Here's a factual anchor. In today's cosmic budget, dark energy accounts for about 68% of the total energy content of the universe. Dark matter makes up about 27%, and ordinary matter, the atoms that form everything we see, only about 5%. The destiny of the cosmos is determined by the balance of these ingredients. If dark energy is truly constant, the universe will continue to expand forever, leading to a fate known as the heat death or big freeze. In this scenario, galaxies beyond our local group will slip beyond our cosmic horizon, their light stretched to invisibility. Stars will burn out over trillions of years, leaving only cooling embers and dead planets. Black holes will slowly evaporate via Hawking radiation over 100 years, leaving nothing but a thin bath of low-energy photons. The universe will be dark, cold, and empty, not because it has stopped, but because it has expanded beyond the capacity for anything to happen. Another possibility is the Big Rip. If dark energy's strength increases over time, a form called phantom energy, its repulsive effect will eventually overwhelm all other forces. Galaxies will be torn from each other, stars ripped from galaxies, planets from stars, and ultimately, even atoms will be shredded. Models of this scenario suggest it could occur in as little as 22 billion years if phantom energy exists. In the last moments, the scale factor of the universe would grow without limit in a finite time, and space-time itself would fracture. On the opposite end of speculation lies the Big Crunch. If dark energy were to reverse sign or weaken enough for gravity to regain dominance, the expansion could slow, halt, and then reverse. Galaxies would begin to approach each other, the cosmic web collapsing inward. Eventually, all matter and energy would be crushed into a hot, dense state, perhaps triggering a new Big Bang. This cyclical view of the cosmos offers an appealing symmetry, but current measurements strongly suggest our universe's expansion is accelerating, making a big crunch unlikely. There are also more subtle possibilities. The universe might coast forever in a state of eternal but slowing expansion, never reaching heat death but gradual, freezing into stasis. Or dark energy could decay into another form of energy or matter, changing the rules of cosmic evolution in ways we can only guess at. From a sensory perspective, imagining these fates is to imagine the night sky transforming. In the far future of a heat-death universe, only the Milky Way Andromeda remnant and its few bound companions will remain visible. Beyond that, there will be no trace of the Great Drift, no hint to future astronomers that a vast cosmos once lay beyond their island of light. The memory of the universe's youth will be erased, not by destruction, but by silence. The acceleration of expansion also sets a hard limit on what we can ever learn. The cosmic event horizon, the maximum distance from which light emitted now can ever reach us, means there are galaxies whose current light will never arrive. As time passes, this horizon shrinks in comoving terms, sealing more and more of the universe away from our view. One day, even the cosmic microwave background will fade, its last photons stretched beyond detectability. Oddly, this makes the present cosmic era special. We live at a time when we can still see galaxies billions of light years away, still detect the CMB, still reconstruct the universe's early history. In a few tens of billions of years, these clues will vanish from view. Civilizations that arise then will have no direct evidence of a Big Bang, no way to measure the expansion, no sign that they are not alone in an endless dark ocean. They will live in what some cosmologists call a cosmic isolation bubble, where only their local cluster remains to be studied. Speculation goes even deeper. Some physicists propose that dark energy could be the manifestation of a dynamic field, a kind of evolving energy that changes its behavior over time. Others suggest it could be a sign that our understanding of gravity breaks down and the largest scales, and that no mysterious energy is needed at all. In these scenarios, our predictions for the universe's destiny could be entirely wrong. Whatever the truth, the expansion is not slowing, and the future will be shaped by its pace. The great web of galaxies will thin, connections will fade, and eventually the visible universe will be reduced to a handful of lights in the dark. The beauty of the cosmos we see today is, in a sense, temporary, a fleeting stage in a story measured in trillions of years. Perhaps that is what makes it so precious. Knowing that this era will not last forever sharpens our view of the galaxies on the horizon, the faint glow of the CMB, the deep fields captured by our telescopes. They are not only windows into the past, but also reminders that the present is a unique vantage point in cosmic time. The universe expands, and in doing so, writes its own ending, whether it be a cold fade, a violent rip, or an eternal unfolding. And we, drifting with it, are part of that story, bound to its destiny. Stand beneath the night sky on a clear, moonless evening, far from the glare of city lights. The dome above you glitters with countless stars, and beyond them, though your eyes cannot see it, lies a lattice of galaxies stretching outward into darkness. That darkness is not empty. It is filled with light that is simply too faint, too redshifted, too far gone to reach you. This is the first hint that what you see is only a small fraction of what exists. The sphere of sky accessible to us is called the observable universe. It is not a physical shell, but a boundary drawn by the speed of light and the age of the cosmos. Light has had only 13.8 billion years to travel since the Big Bang. Yet because the universe has been expanding during that time, the most distant light we can see today comes from sources now about 46 billion light-years away. That distance marks the edge of our cosmic horizon. Beyond that horizon, space continues. Galaxies form and drift. Clusters weave themselves into filaments of the cosmic web. But their light has not had time to reach us. And due to the accelerating expansion driven by dark energy, some of it never will. The observable universe is thus a kind of personal bubble centered on the observer. If you were to stand on a distant galaxy near the edge of our bubble, you would see your own horizon centered on you, encompassing a region much like ours. Every point in the universe has its own observable sphere, overlapping with some and excluding others. There is no universal edge, only local horizons defined by light and time. Here's a grounding fact. The volume of our observable universe contains an estimated 2 trillion galaxies. That number alone is staggering, but it is almost certainly a tiny fraction of the total number of galaxies in all of existence. If space is infinite, as many cosmologists suspect, then beyond our bubble lies an unending expanse, perhaps containing an infinite variety of structures, histories, and even physical laws. The cosmic event horizon complicates this picture. Even within our observable universe, there are regions whose present light will never reach us because the space between us and them is expanding faster than light can traverse. They are visible now only because we are catching light they emitted long ago when they were closer. Any new light they send will be forever stranded. In practical terms, this means the observable universe is not only finite in what it contains, but also shrinking in terms of what will remain visible in the future. Over billions of years, galaxies outside our local group will disappear beyond reach, their last photons stretched into undetectable wavelengths. Speculation takes this boundary into even stranger territory. Some models of cosmic inflation suggest that space beyond our horizon may be radically different from what we know, filled with different particle types, forces, or even dimensions. In the most extreme versions, the universe we inhabit is just one bubble in an infinite multiverse, each bubble expanding into a larger inflating space. The physics in those other bubbles might be wildly unlike ours, and no signal could ever cross from one to another. Other ideas imagine a universe that wraps back on itself in unexpected ways. If space is finite but unbounded, like the surface of a sphere, then traveling in one direction long enough could, in principle, bring you back to your starting point. In such a cosmos, the same galaxy could appear in multiple locations in the sky, its light arriving by different routes. Searches for repeating patterns in the cosmic microwave background have so far found no evidence for such a topology, but the possibility remains an open question. And then there is the truly mind-bending implication of infinity. If space is infinite, and matter is distributed more or less uniformly, then every possible configuration of matter must occur somewhere, not just once, but infinitely many times. Somewhere beyond our observable horizon, there could be an exact duplicate of Earth, down to every detail of your life and every word you've ever spoken. The distance to such a duplicate, if it exists, is thought to be on the order of 115 meters, an absurdly large number, but still finite. Beyond that distance, stranger variations abound. Earths where history took different turns, galaxies arranged in alien geometries, universes where the constants of physics diverge just enough to make life impossible. The existence of realms beyond our horizon is not in doubt. The mathematics of general relativity and the evidence from cosmic expansion both demand it. What remains unknown is their nature. Are they like our patch of space, governed by the same laws, rich with galaxies, or are they utterly alien? The answers may be forever out of reach, locked away by the very fabric of space-time. From a sensory perspective, the idea of the observable universe is like standing on an island in a limitless ocean. The mist at the edge of sight marks the farthest you can see, but the waves continue beyond, unseen and unmeasured. You know there must be more ocean, but you will never touch it, never know its exact shape. And yet, there is comfort in knowing that our bubble is vast enough to contain the whole story of cosmic history as far as we can trace it. Within these 46 billion light-years, we have galaxies forming, colliding, and evolving. We have the birth of stars, the creation of planets, the emergence of life. We have the deep background glow of the CMB, carrying the imprint of the universe's first moments. Still, the boundary haunts us. Every photon that arrives from near the edge of our bubble is a message from a time when the cosmos was young and unfamiliar. Those messages will keep coming for billions of years, but never from farther away than the horizon's reach. Beyond that, the universe remains silent. Perhaps the most humbling realization is this: the vast majority of the universe is, and always will be, beyond our direct observation. No telescope, no matter how powerful, can pierce the limit set by the speed of light and the expansion of space. We can model, we can simulate, we can imagine, but there will always be a veil. And yet, we are part of that larger whole, connected to it by the shared moment of the Big Bang. Every particle here was once in causal contact with particles now impossibly far away. The expansion has separated us, but it has not erased the fact that we share the same origin. Our observable bubble is both a limit and a gift, a reminder that our knowledge, though vast, is incomplete, and that the cosmos, no matter how much we learn, will always hold more mystery beyond the edge of sight. The known universe is already vast beyond human comprehension. 2 trillion galaxies within our observable sphere, each with billions of stars. And yet, this might be only the smallest sliver of reality. Beyond the edges of what we can see lies a realm we cannot measure, a territory governed by possibilities that push the limits of science and imagination alike. If the observable universe is a single chapter, then the rest of the book could be infinite, with stories unlike anything we have known. One of the most straightforward yet staggering possibilities is that space itself is truly infinite. If the geometry of the universe is perfectly flat, as our best measurements from the cosmic microwave background suggest, then it may have no boundaries at all. This would mean that beyond our 46 billion light-year horizon lies more of the same: galaxies, stars, and cosmic structures extending without end. But infinity brings with it the strange consequence of repetition. In an infinite expanse, where matter is distributed more or less uniformly, every possible arrangement of particles will occur, and occur infinitely often. Somewhere, unimaginably far away, roughly 115 meters by one estimate, there could be a region identical to ours in every detail. An Earth with the same mountains and oceans, the same history, the same you reading these words. Beyond that, variations would appear, worlds where history turned differently, or where the laws of physics took another path. But infinity is not the only option. The universe could also be finite, yet unbounded. Like the surface of a sphere, you could travel forever without encountering an edge, eventually looping back to your starting point. In three-dimensional space, this would mean the cosmos has a closed geometry. If this were true, light from a distant galaxy could, in theory, reach us along multiple paths, creating repeating patterns in the sky. Astronomers have searched for such patterns in the CMB, a kind of cosmic hall of mirrors, but so far, no definitive evidence has emerged. Then there is the multiverse hypothesis, which takes speculation to another level entirely. In some versions of cosmic inflation, our universe is just one bubble in an eternally inflating space. Inflation ends in one region, forming a bubble like ours, while continuing in other regions indefinitely, spawning new bubbles forever. Each bubble is a universe in its own right, with its own observable horizon and perhaps its own physical laws. Some might have the same particles and forces as ours. Others could be so alien that even the concepts of matter and light do not apply. If the multiverse exists, it may solve certain puzzles in physics. For example, the strength of dark energy in our universe is incredibly small compared to the value predicted by quantum field theory, smaller by a factor of 10^120, the largest known discrepancy between theory and observation. In a multiverse, this could be explained by a kind of cosmic selection effect. Universes with much stronger dark energy expand so rapidly that galaxies never form, and thus no observers arise to measure them. We find ourselves in a universe with just the right value because only such universes can host life. Other speculative models imagine dimensions beyond the three of space and one of time we experience. In string theory, the fundamental constituents of reality are not point-like particles, but tiny vibrating strings whose different vibration modes produce different particles. For the mathematics to work, string theory requires extra spatial dimensions, perhaps 6 or 7 of them, curled up so small that we cannot detect them directly. In some brain world models, our entire universe could be a three-dimensional brain floating in a higher-dimensional space, with other brains, other universes drifting nearby. Collisions between brains could, in theory, produce events like our Big Bang. There are even ideas that challenge the very notion of continuous space and time. Loop quantum gravity, for instance, proposes that space-time itself is quantized, made up of discrete units at the smallest scale, like pixels on a screen. In such a universe, the fabric of reality has a finite resolution, and the apparent smoothness of space is an illusion born from our limited perspective. Some theories extend speculation into the nature of reality itself. The simulation hypothesis suggests that our universe could be a computational construct created by an advanced civilization. If true, the apparent laws of physics would be the rules of the simulation, and the limits we observe, like the speed of light, might be features of the underlying code. This is not a theory most physicists treat as a working model, but it is an example of how speculation about the infinite can blur into philosophy. And then there are the possibilities that lie entirely outside current frameworks. The universe beyond our observable horizon could be dominated by exotic forms of matter or energy. It could contain structures larger than anything we can imagine. Superclusters spanning billions of light years, cosmic voids so vast that they make the great empty regions we know look small. There might be regions where the arrow of time runs differently, or where what we call space is something else entirely. Even if the broader cosmos is much like our own, its sheer size means it must contain wonders we will never witness. There could be galaxies made entirely of black holes, planets orbiting stars made of quark matter, or civilizations that have arisen, flourished, and vanished long before Earth ever formed. The scales of distance and time beyond our horizon allow for histories that dwarf our own in both grandeur and tragedy. From a sensory perspective, imagining the infinite is like standing on the shore of a fog-shrouded sea. The water stretches beyond sight, and while you can sense its vastness, the details remain hidden. You know the waves continue far beyond the horizon, but what they carry, ships, islands, entire continents, is forever unknown. This unreachability is part of the beauty. The fact that we cannot see or touch the infinite does not diminish it. It deepens its mystery. In every direction, the universe offers not a wall, but an invitation to imagine. We are bounded not by the size of reality, but by the reach of our senses and the lifetime of our light. Perhaps one day, our descendants will find ways to probe beyond our observable bubble indirectly, through gravitational waves from ancient cosmic events, or subtle imprints in the CMB, or mathematical clues hidden in the laws of physics themselves. But even then, there will likely always be more beyond, an unreachable frontier that recedes as we advance. The infinite, whether it exists as an actual boundless expanse, a multiverse of bubbles, or an endless chain of cycles, is not something we must solve to value. It is enough to know that beyond the curtain of our horizon lies more reality than we can contain, and that our brief time under the stars is spent inside a universe that is part of something larger still. The story of the universe's expansion is not only written across the heavens, it is inscribed within us. Every atom in your body, every breath you take, every thought that flickers in your mind carries the imprint of cosmic history. We often imagine the expansion as something happening out there, far beyond the reach of our daily lives. But in truth, we are woven into the same fabric that is stretching, and the journey of the cosmos is the story of our own becoming. Consider the atoms that form you. The hydrogen in the water in your cells was born in the first 3-minute S after the Big Bang, forged when the universe was still a roiling sea of particles cooling just enough for protons and neutrons to bind. The carbon in your muscles, the oxygen you breathe, the calcium in your bones, these were forged in the hearts of long-dead stars, scattered across space by ancient supernovae. Even the iron in your blood came from the violent death of massive stars, detonations so powerful they could briefly outshine entire galaxies. The expansion of the universe allowed these stars to form in the first place, gave them the billions of years they needed to live and die, and scattered their elements across space so that one day they might become part of you. This is not poetry, it is literal, physical truth. When we trace the arc of the universe's expansion, we are tracing the path by which matter organized itself into the conditions for life. Without the delicate balance between the pull of gravity and the push of expansion, stars would never have lived long enough to make complex elements. Galaxies would have collapsed too quickly or never formed at all, and the chemical diversity needed for biology would not exist. And there is another layer. The expansion is not just a stage on which the drama of life unfolds. It is an active shaper of what is possible. In the early universe, expansion happened so quickly that it smoothed space almost to perfection, leaving only slight ripples in density, ripples that later became the scaffolding for galaxies. Without those ripples, there would be no great cosmic web, no chains of galaxies lighting the darkness. Without galaxies, there would be no suns. Without suns, no planets. Without planets, no oceans, no forests, no human eyes to see the stars. The universe expands in ways we cannot feel directly. Between the molecules in your hand, the effect is negligible, drowned out by electromagnetic forces. Between the sun and earth, gravity holds tight, and the expansion has no measurable pull. But over billions of light years, the swelling of space is the dominant motion, carrying galaxies away from one another in the Great Drift. And yet, the space between your atoms is part of that same fabric. The same laws that govern the expansion of the largest structures also govern the emptiness within you. You are not separate from the process. You are an instance of it. Philosophically, this binds us to the universe in a profound way. The expansion is not a distant phenomenon. It is a reminder that we are continuous with the cosmos. We are not passengers riding in a vessel of space. We are the vessel, shaped from the very matter that the universe assembled, carried forward by the same currents that separate galaxies. Speculation invites an even deeper connection. If the universe is infinite or part of a multiverse, then the atoms that make you could be arranged in countless variations across the cosmos. Somewhere beyond our horizon, there could be another version of you, perhaps almost identical, perhaps wildly different, thinking similar thoughts under a different sky. In an infinite unfolding, identity becomes not just a personal fact, but a cosmic pattern, repeated and reimagined across space-time. From a sensory perspective, try to imagine the expansion not as a balloon swelling, but as a slow, deep breath taken by the cosmos itself, one that has lasted for nearly 14 billion years. With every moment, more space is created, and within that space, possibilities multiply. You are a ripple in that breath, a temporary configuration of matter and energy brought into being by its motion. When your body returns to the earth, your atoms will scatter and eventually take part in other forms. Perhaps another life, perhaps the dust of a distant comet, perhaps the atmosphere of a world not yet born. The expansion will carry them onward into futures you cannot see. There is a quiet, humbling beauty in knowing that you are made of elements older than the earth, older than the sun, older than the Milky Way itself. You are, in a very real sense, a piece of the universe looking back on itself. Matter become aware, asking questions about its own origins. The expansion has made this possible not through intention, but through the interplay of simple rules repeated across unimaginable scales and times. Even as we contemplate the future, the heat death, the big rip, or some fate we have not yet imagined, we can take comfort in the fact that the expansion has given rise to consciousness at least once. Whether that consciousness exists elsewhere is a question as open as the universe itself. Perhaps there are other beings under other skies, also looking outward, wondering what lies beyond their own horizons. If so, then in the grand sense, we are not alone in this experience, even if we can never meet them. In the far future, when the sky grows emptier and the great drift carries most galaxies beyond reach, civilizations will have only the stars of their own cluster to study. The story of the expansion will be harder to uncover then, written in fewer clues. But here, now, we live in a privileged moment, one in which the evidence of our origins surrounds us in every direction. The faint glow of the cosmic microwave background, the red shift of distant galaxies, the large-scale map of the cosmic web, all are chapters in the same story, and all are still visible to us. We can think of this as a gift of timing. Out of all the billions of years the universe will exist, we happen to live in an era when the expansion is both measurable and meaningful to our understanding. The window will not stay open forever, but it is open now, and through it we can see that we are participants in a process so vast that it folds the personal into the cosmic. And so when we speak of the expanding universe, we are also speaking of ourselves. Our cells, our thoughts, our histories are bound into this widening tapestry. The same laws that carry galaxies apart have carried us into being. The same space that grows between clusters of stars exists within the atoms of our blood. The universe expands within us as surely as it expands around us. Perhaps that is the quiet truth hidden at the heart of all this exploration, that the boundary between us and the universe is an illusion. There is no outside to the cosmos. and there is no outside to our belonging within it. We are not simply in the universe, we are of it, temporary forms in an unending act of becoming. The expansion continues, and with each moment, we continue with it.